Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
All right, this is chapter 3, section 5. So this is 3.5. And this is implicit differentiation. So first, let's consider the following scenario. Let's say that I've got the equation of a circle like that, right? And the equation of a circle, well, what is it? It's x minus h squared plus y minus k squared is equal to r squared, right? That's the equation of the circle. In here, this is not a function of x. It's not a function of x, fails vertical line test. All right, so not a function of x. And because it's not a function, we cannot take the derivative. Let me rephrase that. We cannot easily find the derivative. What do I mean by that? Well, let's consider that we would want to find the equation of this tangent line, right? Or the equation of, well, let's do a different point, or the equation of this tangent line, right? And either way, well, we know that when we need the equation of a tangent line, we need the slope, right? And to find the slope, we find the derivative. But the derivative was only defined for functions of x. So how do we do it there? All right. So essentially here I'm saying this is not a function of x, so how would we find the derivative? Similarly, we can have equations or graphs that look like this, right? In here, the equation of this graph is y cubed plus y squared minus 5y minus x squared is equal to negative 4. But again, this is not a function. Right, this is function. This is not a function. Why? Because fails the vertical line test. But we still are interested in being able to find slopes. Right? Because we still want to be able to find the equations of these tangent lines. We want to find the rates of change there. So how do we do it? Well, that's what implicit differentiation is about, is being able to deal with these scenarios. All right, how would we find the derivative? And the process, well, it's called implicit differentiation. That's not how you spell process. I think that's how you spell process. I have no idea. Anyway, the process is we treat y as a function of x. And apply the chain rule. Right, we treat y as a function of x and apply the chain rule. So let's see what we mean by that. Let's say that I was working with that equation, y cubed plus y squared minus 5y minus x squared is equal to negative 4. Let's say that I was interested in finding the slope of this, right? So we're going to say find dy dx. Well, what we're going to say here is, well, since we're treating y as a function of x, let's let y equal f of x, all right? And if I do that, well, then dy dx, the derivative, would be f prime of x, right? I mean, that's just notation, but let's see what we can do here. I'm going to have here f of x squared plus f of x, sorry, this should have been cubed, f of x cubed plus f of x squared minus 5 times f of x minus x squared is equal to negative 4. And if I take the derivative of this equation, well, on the left side, what do I get? I end up with 3 times f of x quantity squared, right? Because the derivative of something cubed is 3 times that something squared. And then by the chain rule, times the derivative of the inside. Similarly, I end up with 2 times f of x to the 1 times f prime of x, and that is a prime there. And then minus 5 times f prime of x, right? Because the derivative of f of x is f prime minus 2x is equal to 0. All right. So now, since the question was find dy dx, that means we're looking for f prime of x. So let's solve for f prime of x on this equation. So I've got f prime of x, and we're going to factor it out of here, here, and here, right? And what are we left with? We're left with 3 times f of x squared plus 2 times f of x minus 5, right? Just factor it from the first 3 terms. This negative 2x, move it to the other side, so I end up with equals 2x. So that now, well, solving for f prime, I end up with f prime of x is equal to 2x over 3 times f of x squared plus 2 times f of x, 2 times f of x minus 5, right? And, well, since we said that f prime is dy dx and f of x is just y, we can say here that dy dx is equal to 2x over 3y squared plus 2y minus 5. All right. Now, in here, this is essentially how we think about this, all right? Because we're treating y as a function of x. That's what we mean when we say that. Treat y as a function of x and apply the chain rule. But that's not really the process of how we normally would do this, all right? So let me show you how we would normally do this kind of problem where you're finding the derivative. So we have y cubed plus y squared minus 5y minus x squared is equal to -4, right? And let's go ahead and take the derivative here. Well, I've got y cubed, the derivative, 3y squared, all right? But now I need to multiply by the derivative of the inside because I'm treating y as a function of x. So 3y squared times dy dx plus the next one, the derivative of y squared, 2y. But now I need to multiply by the derivative of the inside, right? Because this was something squared. So the derivative of y with respect to x is dy dx minus 5 times the derivative of y is just dy dx minus the derivative of x squared, -2x, the derivative of -4 is 0. At that point, I see that I've got dy dx on these 3 terms, so we can factor that out, and I end up with dy dx times 3y squared plus 2y minus 5, right? I just factor out these 3, move the -2x to the other side, so I end up with equals to x, so that dy dx is equal to 2x over 3y squared plus 2y minus 5. Excuse me. So that's what we get there, all right? And that is a process. Now, notice that every single time I took the derivative of something that involved y, I multiply by dy dx, all right? That's essentially what you want to remember. Anytime you take the derivative of anything that involves y, we multiply by dy dx. So let's do a couple of examples here. Find the equation of a tangent line. Find the equation of the tangent line at the given point. So here we go. Let's say that I had this equation, x squared over 2 plus y squared over 8 equals 1. And we want to find the equation of the tangent line at the point 1, 2. All right. So here we go. What we're going to do here first is, well, let's take the derivatives, right? Why do I want to find the derivatives? Because we need the equation of a tangent line, a line, we need the slope. And the slope is dy dx, so, right? So that's what we need. We need the slope. So, all right, so let's take the derivative. So the derivative of x squared over 2, 2x over 2, plus the derivative of y squared over 8, 2y over 8 times dy dx, the derivative of 1, 0. So reducing here, we end up with x, well, x over nothing, x plus y over 4 dy dx is equal to 0. Move the x to both sides, y over 4 times dy dx is equal to negative x, so that dy dx is equal to divide by y. That's a divide by y. So we had negative x, we divided by y, and then multiply by 4. So we really have here a negative 4x, right? Multiply by 4, divide by y. All right. So that is dy dx. So now our slope is going to be dy dx evaluated at our point. All right, that's how we read that. Evaluated at that point. So we're going to say this is negative 4 times 1 over 2, giving me negative 2. And now that I've got my slope, well, I had a point already. I have a point and a slope. So let's see what we do with that. So our slope was negative 2, and our point was 1, 2. So to find the equation of a tangent line, we'll use a point-slope equation. So y minus y1 is equal to m times x minus x of 1. So we have y minus 2 is equal to negative 2 times x minus 1. Distributing the negative 2, negative 2x plus 2, add 2 to both sides, plus 2, not plus 4. Add 2 to both sides, there we go. And that way it's still there. So I end up with negative 2x plus 4, all right? And that's the equation. So the process, again, is still the same idea of finding to find the equation of the tangent line. It's just we're using implicit differentiation to find these things out, right? And graphically speaking, let's see what we found here. You may or may not recall that this equation, x squared over 2 plus y squared over 8, is an ellipse. It looks something like that. Oh, let me make that better. There we go. It's an ellipse, all right? X squared over 2 plus y squared over 8 is equal to 1, all right? And what we found here is that at the point 1, 2, let's say that's 1, and this up here is 2. At that point 1, 2, we had this tangent line, which happens to be y equals negative 2x plus 4. And that makes sense, right? Negative slope crossing through 4. All right, so that's what we just found there. Okay? So let's do another example. All right? So that was example B. So example C. Let's say that I had, so semi-tech instructions, but now I've got y squared times x squared plus y squared is equal to 2x squared, and now we're doing it at the point 1, 1. All right. So again, we need the slope, right? To find the equation of a tangent line, we need the slope. We already have the point, and the slope is given by dy dx. So we need dy dx. So let's see what we to do here. Well, before we actually start, I want to distribute this y squared. So what do I get? I end up with x squared times y squared plus y to the 4th is equal to 2x squared. All right. Now, recall that when we're finding the derivatives of equations like these, we need to treat y as a function of x. Treat y as a function of x. So in here, in this piece right here, x squared is a function of x, y is a function of x. So in here, since we're treating y as a function of x, what we've got here is the product of two functions of x. So I've got a product of two functions of x, which means I need to use the product rule to find these. I'm going to call this u and that v. And recall that the derivative with respect to x of the product of two functions of x, uv, is u prime v plus v prime u. All right. So let's go ahead and apply that here. So what does that mean? So the derivative of this equation, well, the derivative of the first, right? And here I need to do the product rule before I can even consider the rest of that. So perhaps that part I'll do in blue. So the derivative of the first, 2x, times the second, y squared, plus the derivative of the second, 2y times dy dx, right, by implicit differentiation, times the first. All right, so in there's my product rule. And then the rest of it, well, plus 4y cubed times dy dx is equal to 4x. All right. Next thing that I'm going to do is, I see that we've got dy dx in those two places, so I'm going to factor out a dy dx. All right. I'm also going to move, well, let's factor out that out first. And what am I left with? So if I factor out a dy dx out of here, I'm left with 2x squared y, right? We like to put them in alphabetical order. And the other one, we end up with 4y cubed. I'm going to move this to the other side, so I end up with, this is equal to 4x minus 2xy squared. At that point, divide both sides by this thing, so I end up with dy dx is equal to 4x minus 2xy squared over 2x squared y plus 4y cubed. All right. So that's as far as the derivative. I mean, what else can we do here? I see that we've got all even numbers everywhere here. So if I multiply by 1 over 2 over 1 over 2, in other words, divide everything by 2 here, I end up with 2x minus xy squared over x squared y minus 2y cubed. All right. Now, we just found dy dx. But what we were looking for was the equation of the tangent line. So, I mean, we needed dy dx, that was our slope, but now we need to evaluate it at that point. So in here, we can say, well, this evaluated at the point 1, 1. Well, what do we get? We end up with 2 times 1 minus 1 times 1 squared over 2. Where did I get that 2 from? I don't know. So over 1 squared minus y minus 2, not minus y squared times y, there we go, but y was 1, minus 2 times 1 cubed, there we go. That was a struggle for some reason, I don't know. But anyway, what does this give us? This gives us 2 minus 1 over 1 minus 2. Well, not 1 minus 2. Look at this. I missed that plus. That's a plus. That's a plus. That's a plus. So 2 minus 1 over 1 plus 2. There we go. Way better. 1/3. All right. So that's my slope. dy. So that's my slope, right? My slope. So I have a slope of 1/3, and we had this at the point 1, 1. So now we can go ahead and apply the point slope formula, right? Because I have a point and a slope and a point. So I have y minus y sub 1 is equal to m times x minus x sub 1. In this case, that means y minus 1 is equal to 1/3 x minus 1. Distribute the 1/3, so I end up with 1/3 x minus 1/3, add 1. So I end up with y is equal to 1/3 x plus 2/3, right? Negative 1/3 plus 1 is 2/3. And that's the equation of that. So let's see graphically what we found. So first, let's draw the equation here, and it looks something like this. All right, looks something very similar to that. And well, so that was our equation of y squared times x squared plus y squared is equal to 2x squared. And what we found was that the point 1, 1 we had this equation. We had this line, and this is y equals 1/3 x plus 2/3. All right. Cool. All right, so let's take it up a notch. Let's make this a little bit harder. All right. So that was example C, right? I think. Yes, C. So let's do example D. So example D. So here, example D is, let me change that color. So we've got x squared plus y squared squared is equal to 4x squared y. All right. So again, we're going to find the equation of the tangent line of this, but this time we're going to do it at the point radical 3/4, comma 3/4. So, all right. So a few things to notice here. First, notice that in here, I once again have a product rule situation, right? Because I've got the product of two functions of x, because we treat y as a function of x. Not just that, but on this side, I'm going to have the chain rule because I've got something squared, right? So in here, I'm going to have to use the chain rule. So the product rule and the chain rule. So let's see what we get here. Taking the derivative now, all right? And again, we need the derivative because we need the slope. And the slope is given by dy dx, right? So taking the derivative, I end up with 2 times x squared plus y squared times the derivative of the inside, 2x plus 2y dy dx. Notice I multiplied by dy dx because I took the derivative of y. And on the other side, well, applying the product rule, the derivative of the first, 8x, times the second, y, plus the derivative of the second, 1 times dy dx, in other words, just dy dx, times the first, 4x squared. All right. And now, notice I've got dy dx on both sides of these things, but not just that, I've got a dy dx on this left instead of this product here. So the very first thing I need to do is expand that product. All right. Well, before that, let's see. I'm going to distribute this 2 into here. So I end up with x squared plus y squared is equal to 4x plus 4y dy dx. The next thing I'm going to do is I'm going to FOIL this. So I end up with 4x cubed, right? X squared times 4x is 4x cubed, plus 4x squared y dy dx, plus 4xy cubed, I meant y squared, right? And distributing this y squared, plus 4y cubed dy dx. So in there, all I did was FOIL this stuff out. And we've got that being equal to, on the right side, well, let's rewrite this a little bit. 8xy plus 4x squared dy dx. All right. Now, let's see. I see that I've got dy dx all over the place here. So I'm going to factor out that dy dx out of everything. So what am I left with? I'm left with dy dx times, here's the dy dx, so I'm factoring out of there, so I'm left with 4x squared y plus, I've got a 4y cubed there, right, with this dy dx, and 4y cubed, and I have a dy dx on this side too. But notice that's on the other side of the equal sign, so to bring it on this side, I have to subtract it, so I have minus 4x squared. On the other side, I still have that 8xy, and what else? I could bring this 4x cubed to the other side, so minus 4x cubed. I can bring this 4xy squared over as well, so minus 4xy squared. At that point, well, that gives me now that dy dx is equal to 8xy minus 4x cubed minus 4xy squared over 4x squared y plus 4y cubed minus 4x squared. The next thing I notice here is that everything here everything here is divisible by 4, right? So I can multiply everything here by 1 over 4. In other words, think about it as dividing everything by 4. Here I'm using it as multiplying it by 1, right? But this one is 1/4 over 1/4. And well, what does that give me? That gives me 2xy minus x cubed minus xy squared over x squared y plus y cubed minus x squared. All right, all I did there was multiply everything by 1/4, right? So now that is just dy dx, but we need dy dx at that point. So now dy dx, so our slope is going to be dy dx evaluated at the point radical 3 over 4 comma 3 over 4. So let's see what we get here. We have 2 times radical 3 over 4 times 3/4 minus radical 3 over 4 cubed minus radical 3 over 4 times 3/4 squared. All of this over, on the bottom I'm going to have radical 3/4 squared times 3/4 minus radical 3/4. That's not true. We're plugging in y, so just 3/4. 3/4 cubed minus radical 3/4 squared. All right. So now, at that point, let's simplify this a little bit. All right. Let's see what we get here. In this first part, 2 times 3 is 6, so we get 6 radical 3. On the bottom, 4 times 4 is 16. Minus, on this next part, 4 to the third, that's 64. Radical 3 to the third, well, that's radical 3 times radical 3 times radical 3, which is just 3 radical 3. So in here, I end up with 3 radical 3. Minus, in here, 3 squared is 9. So I end up with 9 radical 3 on top. 4 squared times 4, well, that's going to be 4 cubed. And we just said that was 64. Over. Radical 3 squared, that's 9. 9 times 3 is 27. 4 squared times 4, we just said that was 64. Minus 3 cubed is 27. Hold on, I messed up here. Radical 3 squared is 3. Right, because it would be radical 9, excuse me, it would be radical 9, right, and radical 9 is just 3, so 3 times 3 is not 27, 3 times 3 is 9, all right, so 9 over 64, all right, good, everything's great with the world now. 3 cubed, 27, 4 cubed, 64, all right, radical 3 squared, 3, 4 squared, 16, all right, now, the next thing I'm going to do here is, well, I see a whole bunch of fractions, right? So I'm going to multiply by the least common denominator of all those fractions, which is 64. So I'm multiplying by 64 over 64, right? Because that fraction right there is just equal to 1, and we know that we can multiply by 1 and not change anything, right? So when I distribute that 64, well, what do I end up with? Well, notice that 64 times 1/16 is just 4, right? That's just 4. So what I really have here, 64 times this first part is really, well, the 16 and the 64 and the 16 reduce. So 4 times 6 is 24. So 24 radical 3 minus, and here that 64 just cancels out. Similarly on that last one. On the bottom, 64's cancel out. 64's cancel out. 64 and 16 reduce to being 4, so 4 times 3 is 12. All right. So now 24 radical 3 minus 3 radical 3 minus 9 radical 3, that's going to be 12 radical 3. On the bottom, 9, whoa, hold on. I just realized it's supposed to be a plus sign. Look at this. Plus, 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 plus. All right, 9 plus 27 is 36 minus 12 is 24. Making this reduce to be radical 3 over 2. All right, radical 3 over 2. So that's our slope. Our slope here was radical 3 over 2. And if you recall, what we were looking for here is the equation of the tangent line at the point radical 3/4, comma 3/4. So now we're going to say y minus y sub 1 is equal to m times x minus x sub 1, right? And there I'm just applying the point slope formula. And at that point, if I distribute those things correctly, right, well, what do I end up with? I end up with radical 3/2 times x minus radical 3 times radical 3 is just 3. 2 times 4 is just 8. Add 3/4 to both sides, so plus 3/4. And then negative 3/8 plus 3/4, well, that's going to give me that y is equal to radical 3/2 x plus 3/8. All right. And now what did we find here? Let's look at the visual here. All right. And the visual here is, well, we've got a function here, not a function, an equation here that looks as follows, or approximately as follows. Oh, that's bad. Let's draw this again. Something like this. All right, kind of. Close enough. So in here, we've got at the point, well, let's do it this way. This is 1. This is 1. So the point that we were working with was radical 3/4 and then 3/4. So at this point, we found the equation of the tangent line. So the equation of the tangent line here was y is equal to radical 3/2 x plus 3/8. Let's just, and that equation in blue was x squared plus y squared squared is equal to 4x squared y. All right. All right. Next one. So that was D. E. And let's do that in white. E. So find dy dx for sine of y is equal to x. All right. So, okay. In here, let's start with how are we going to do this? Well, on the right side, it's just regular derivatives. On the left side, we're going to have to do implicit differentiation. All right, we need to do implicit differentiation here because, well, we have a function inside a function, right? And so that's going to require the chain rule, but that function is a function of y. So that's going to require the implicit differentiation. Implicit differentiation. There we go. So let's go ahead and do this. So on the left side, the derivative of sine of y. Well, the derivative of sine is cosine times dy dx. The derivative of x is 1. So that tells me now that dy dx is equal to 1 over cosine of y. But now, what we want to see here is, well, let's recall the following. We know that sine squared theta plus cosine squared theta is equal to 1. So that really tells me that cosine squared theta is equal to 1 minus sine squared theta, which means that cosine theta is equal to plus or minus the square root of 1 minus sine squared theta. If we ignore the negative, and the reason we're ignoring the negative is because we're working with, we want to work with a function here, so we're going to say let cosine theta be equal to just the positive version, right? So if we do that, well, in here, cosine of y would be this idea, right? But instead of with thetas, with y's. So we get here is this is going to be 1 over the square root of 1 minus sine squared of y. But we know what sine of y was. Sine of y was x. So in here, this gives me 1 over the square root of 1 minus x squared. All right. So that's our dy dx. That's your final answer. All right. So that was E. F. Let's say that I had x squared plus y squared is equal to 36, right? But here I'm going to say find the second derivative of y with respect to x. So here we go. So first, let's go ahead and take derivatives. So the derivative here ends up being 2x plus 2y times dy dx is equal to 0, right? So in here, solving for dy dx, subtract the 2x over, so I end up with 2y dy dx is equal to negative 2x, right? Negative 2x. Dividing both sides by 2y gives me now that dy dx is equal to negative x over y, right? Notice I reduced those twos already. So negative x over y. Okay, but that was the first derivative. And the question was to find the second derivative, right? Well, in here, notice what we've got here. We've got the quotient of two different functions. So we need to use the quotient rule, all right? And when we do this, well, we need to make sure that we apply implicit differentiation to the bottom. If you recall here, and I'll remind you that the derivative with respect to x of the quotient of two functions is u prime v minus v prime u all over v squared, not u, all over v squared, all right? So let's go ahead and apply that. So in here, the second derivative now, so that was just some side work. But now the second derivative, so the derivative of the top, negative 1, times the bottom, y, minus the derivative of the bottom. The derivative of y is going to be just dy dx, the derivative of the bottom, times the top, negative x, all over the bottom squared. Distributing this, distributing a little bit, so negative 1 times y is negative y, negative times a negative is positive, so x times dy dx over y squared. But now, dy dx, we have what that is. Dy dx is negative x over y. So I'm going to replace that. So here I have negative y plus x times negative x over y, all of this over y squared, right? At this point, well, let's see what we get. We end up with negative y minus x squared over y, all of this over y squared. At this point, we're going to say let's multiply by 1. I don't want to have fractions over fractions. So I'm multiplying by y over y. And at that point, I end up with negative y squared minus x squared over y cubed, right? And if I factor a negative out of this, I end up with negative, let's put it in alphabetical order, x squared plus y squared over y cubed. But we're still not done. Look at this, how convenient. We have what x squared plus y squared is. So in here, look at that, I forgot the square. X squared plus y squared. So we had what x squared plus y squared is, and it was 36. So we end up with negative 36 over y cubed. So in here, our second derivative was just negative 36 over y cubed. All right. All right, so now G. Let's say, actually, before I do that, let's talk about something called logarithmic differentiation. And as the name would imply, it's taking derivative using logarithmic methods, right? So that means using logs. And in here, first I want to remind you of the rules of logs, and I'll do them with ln, all right? So ln of a plus, ln of a times b is ln of a plus ln of b. Ln of a over b is ln of a minus ln of b, and ln of a to the b is just b ln of a. Now, in here, we're gonna be using these rules um, to help us, right? So let's do example G. Let's see what we mean. And in here, I'm gonna say find dy dx, given that y is equal to x times x minus 1 to the 3/2 over x plus 1 to the 1/2, where x is greater than 1. All right. Now, in here, this x being greater than 1, well, that's just a technicality so that we can actually have a domain here workable, a workable domain. All right. So let's see what we get. The very first thing that I see here is if I were to take the derivative of this thing on the right here, well, we've got a quotient and we've got a product. So we would technically need to be using the product and the quotient rule within each other, and also the chain rule throughout. So let's not do that. So what we can do here is we can say, well, if I take ln of both sides, I end up with this following statement: ln of y equals ln of x times x minus 1 to the 3/2 over x plus 1 to the 1/2. Now, at that point, I'm going to apply the rules of logs, right? I'm going to apply these three rules up here in blue into this statement. So the left side stays ln of y. The right side becomes ln of x plus 3/2 ln of x minus 1 minus 1/2 ln of x plus 1. So far, we have all we've done so far is expand that expression using rules of logs, right? Now, the next thing that I'm going to do here is, well, let's go ahead and take this derivative, all right? If I go ahead and take this derivative, well, what do I end up with? On the left side, the derivative of ln of y, well, that's going to be 1 over y times dy dx by implicit differentiation. On the right side, the derivative of ln of x is 1 over x plus 3/2 times 1 over x minus 1, technically times 1, right, because of chain rule, the derivative of the inside, minus 1/2 times 1 over x plus 1, and again technically times 1 on there. So what do we really have here? Well, that's going to tell me that dy dx is going to be y times all of that, right? I'm bringing this 1 over y to this side by multiplying everything by y. And what is that? It's 1 over x plus 3 over 2 times x minus 1 minus 1 over 2 times x plus 1. And lastly, well, we know what y was, right? At the very beginning, we knew we had this definition for y. So what we can say here now is that dy dx would be equal to, well, the entire expression, x times x minus 1 to the 3/2 over x plus 1 to the 1/2, and that times 1 over x plus 3 over 2 x minus 1 minus 1 over 2x plus 1. All right, and notice again, all I did there was replace this y here. And the reason I've got that y there is because I multiplied both sides by y to get rid of this, it on this side. All right. At that point, we're gonna leave it there. All right, we're gonna stop there. as far as this problem goes. We could technically come up with a common denominator and see how this might reduce and whatnot, but no, don't go through that trouble. This is good enough. All right, that is a good enough final answer. No reason to go any further. So that's one example, and that was G. So H. Let's see another example. Let's say that I had y is equal to cosine cubed of x times 3x squared plus 7x minus 1 to the 1/3 over 2 to the 3x. That's not what I meant to write. I meant to write, oh, that's fine, 2 to the 3x. That's good enough. All right. So what are we going to do here? Well, again, if I were to just take the derivative of this, well, this would be a quotient rule with a product rule with chain rules. So that would be very complicated. So what we can do here is we can go ahead and start by taking the natural log of both sides, all right? So we're going to do logarithmic differentiation. And when we do that, well, this statement becomes 3 times ln of cosine of x plus 1/3 times ln of 3x squared plus 7x minus 1 minus ln of 2 to the 3x. All right. All right. Actually, I want to rewrite that. I don't want to write it that way. I want to write it as 3x ln of 2. There we go. All right. So now, let's go ahead and take derivatives here. Let's see what we get. The derivative of ln of y, well, that's going to be 1 over y times dy dx by implicit differentiation. The next thing, 3 times the derivative of ln of something is 1 over that thing, and then by the chain rule times the derivative of the inside. The derivative of cosine is negative sine, right? Next thing, plus 1/3 times the derivative of ln of something is 1 over that thing, times the derivative of the inside, 6x plus 7, minus, in here, look at this, 3 ln of 2 times x. If I had something like 5x, its derivative would be just 5, right? So essentially here we have the same scenario where 3 ln of 2 is just a number, so we could treat it like 5. And in here, 3 ln of 2x, its derivative, is just 3 ln of 2. So at that point, well, what can we say here? That's gonna tell us that dy dx is gonna be equal to y times this entire thing. So 3 times 1 times negative 1 is negative 3. Sine over cosine is tangent. Plus in here, let's write this as 6x plus 7 over 3 times 3x squared plus 7x minus 1. And then minus 3 ln of 2. All right. And at that point, well, we know what the value of y was, right? The value of y was this entire thing up here. So what we can do is we can replace that down here, right? This y right here. So we're going to say now that dy dx is equal to, well, this entire thing times this entire thing. And again, in there, what I'm doing is copying and pasting them. Oh, maybe we need to make that a little bit smaller. Something like that. You know what? I'll make this one smaller too. All right. And that would be our final answer. All right. We could try to come up with common denominator on the right and try to like manipulate this even further, but there's no reason to. This is a good enough final answer. All right. So all right. So that was example H, right? Yes. Example I. Example I. Let's say that I had y equals x to the 2 over x for x being greater than 0. All right. So let's go ahead and start this out. So what do we do? What do we do? Let's do the same exact thing as before. Actually, before, let me show you the wrong thing to do. All right, so the following thing is wrong. And I want to show you the wrong thing to do only because it's a very common mistake. So I had the y equals x to the 2 over x. It's a very common mistake to do the following. Say that dy dx is, we'll bring the exponent to the front, 2 over x, and subtract 1 from the exponent. That is not the way to do this, all right? This rule only is it's using the following rule incorrectly. All right, this rule over here, it's true. When I have x to a number, it's the derivatives n times x to the n minus 1. But this up here is not a number, it is a function. So this idea does not apply. All right, so this is wrong. So don't do this. And again, this is a very, very common mistake. So let's see the correct thing to do. All right, and correct. So that's the correct thing to do. So I start with y is equal to x to the 2 over x. I'm going to start by taking the natural log of both sides. So I end up with ln of y is equal to 2 over x ln of x. All right, I'm going to write that as 2 ln of x over x. And now I'm going to take the derivative. All right, I'm going to take the derivative. But notice that on the right-hand side, I've got a quotient. All right, I've got the quotient of two functions. So I'm going to be using the quotient rule. So now, the derivative of the left, the derivative of ln of something is 1 over that something times the derivative of the inside. So that's dy dx, right? Over here, quotient rule, the derivative of the top, 2, oh, that's not true, 2 over x, there we go. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So that gives me now that dy dx is equal to multiply the y to this side. So y times, reduce this a little bit. So I have 2 minus, right? So that 2 is because these x's cancel out. So 2 minus 2 ln of x, all of this over x squared, right? But we had a value of y. We had a value of y. Y was x to the 2 over x. So what we say here is this is really going to be equal to x to the 2 over x times 2 minus 2 ln of x over x squared. All right, and we could leave it at that. All right, there's no reason to really go any further. That would be our final answer. All right, algebraically, yes, there's more things that we could do here, but there's no reason to go any further here. All right, so that was I. Let's do a similar one, J. Let's say that I had y equals to sine of x to the cosine of x. All right, and we're going to start this in the same exact way that we did just this last one. All right, and again, notice that we have a function in the exponent. All right, so what we're going to do here is logarithmic differentiation to get rid of that. All right, so in general, that's a good rule of thumb. If you have a variable in the exponent, you probably need to do logarithmic differentiation, unless you had something like a to the x, right? Those we know how to take the derivatives of. But if we had a function to a function, logarithmic differentiation. So start by taking the natural log of both sides, right? All I did there was apply the natural log of both sides. The next thing I see there is that on the right-hand side, I've got a product of u and v. So I need to use the product rule. So on the left side, the derivative of ln of y, 1 over y dy dx. On the right side, product rule, the derivative of the first, sine of x, times the second, ln of sine of x, plus the derivative of the second, 1 over sine of x, times the derivative of the inside. The derivative of sine is cosine, so cosine x, and then that times the first, cosine x. All right. At that point, multiply both sides by y, right? Because we want dy dx by itself. So dy dx is going to be equal to y times, I'll write this as, hold on, the derivative of cosine is negative sine, sorry, negative sine, there we go. So negative sine of x, ln of sine of x, plus, and I'll write this as cosine square of x over sine of x, all right? At that point, well, we know what the value of y was. So I have dy dx is equal to, y was ln, no, not ln, sorry, it was sine to the cosine of x, right? There it is, sine to the cosine of x. So we have here sine of x to the cosine of x times, and I'll write this as negative sine of x ln of sine of x plus cosine squared over sine. Well, cosine over sine is cotangent, so I have cotangent x times a cosine x left over, right? Cosine over sine is cotangent, and a cosine left over. And that will be our final answer. All right. So that concludes 3.5 as far as the examples go. Now, I do want to mention, or I do want to do some proofs that I mentioned that I was going to do in this section. So these are proofs from 3.4 that we didn't have the tools to see why they were true. So here, first I'm going to prove that if y is equal to a to the x, then dy dx is equal to a to the x ln of a. All right. So let's start with that. So I have, well, the very first thing I'm going to do here is I'm going to take the natural log of both sides. So ln of y is equal to x ln of a. Then take the derivative of both sides, applying implicit differentiation when needed. So in here, I end up with 1 over y dy dx is equal, on this side, ln of a is just some number. So some number times x, the derivative is just that number. And then that tells me now that dy dx is going to be just y times ln of a. But then y was a to the x, so I get a to the x ln of a, all right, which gives us that that derivative. So that's that one. I also want to prove the other one. So if I have the other one that I mentioned in a prior video was if I have y is equal to log base a of x, that gives us that dy dx is equal to 1 over x ln of a. All right. So let's see what to do here. I'm gonna sort of do the exact opposite as what we've been doing. Instead of doing taking the log of both sides, actually, yeah. So instead of taking the log of both sides, the very first thing I'm gonna do is make this exponential. So I have a to the y is equal to x. And now taking the derivative of both sides. Well, I know what the derivative of a to the y was. I just did that up over here. But so we're gonna end up with a to the y times ln of a. And then by implicit differentiation, I took a derivative of something that involved y, so I had to multiply by dy dx, and that's going to be equal to 1, right? The derivative of x is just 1. And at that point, well, ln of, this is going to be dy dx is going to be 1 over a to the y times ln of a, but a to the y is just x. So here I end up with 1 over x ln of a. And there you go. All right. All right. So that was proving those. Now I'll call it an end to this video. So this was the end of 3.5.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.